So in daily work 4, you had this table to work with. And the question that I asked you about this table is this operation associative? Is star associative? And again, remember what associative means. There's this implicit quantifier, not implicit, we're making it explicit, for all A, B, and C. We need to have A star B, quantity star C, equals A star, quantity B star C. Okay. And almost everyone looked at this table and said, yeah, it's associative. A few of you checked at least 1 or 2 cases. A couple of you checked like 6 or 8 cases. Couldn't find any way to violate this for all. But again, because there's 3 elements that I'm operating on here, I have 3 choices for A, 3 choices for B, 3 choices for C. So if I wanted to brute force guarantee this is associative, I have to check 3 times 3 times 3, 27 different cases. None of you checked 27 cases. And yet many of you concluded this was associative. So I kind of scratched my head at that a little bit. So what I want us to have the opportunity to do here is actually look at 4 different properties: the associative property, the commutative property. Then I also want us to talk about identity and talk about inverses. What cancels what? So before I turn you loose on associativity and commutativity, let's get the low-hanging fruit out of the way. Can you find an element in this multiplication table that behaves like the identity, like an identity, sorry, that leaves everything it operates on unchanged? Casey?
X.
X. How can you tell?
X times X is itself, and X times anything else is the other thing.
Yeah. So just again, looking inside the table of products, quote-unquote products, right? The first row, XYZ, first column, XYZ, those line up exactly with the elements on the outside of the table. So clearly X, whether it operates on the left of an element or whether it operates on the right of an element, is leaving those elements unchanged. So we have an identity. That's good. What about Y or Z? Are either of those also an identity? Caitlin's shaking her head. Why?
Because they always change what they're being multiplied by.
Yeah, something, right. They always, each of those elements changes something that it operates on, right? So for identity, there's also this implicit quantifier. Something is an identity if for all, let's say for all R, X star R is supposed to equal R, which is supposed to equal R star X if it's an identity on both sides. Right? And so it's this for all clause here that identities need to satisfy. And so as soon as we find one example of something that Y changes when it acts upon it, so Y actually doesn't change, it does change X, right? It changes X into Y. It changes itself into X. So both Y and Z are changing something when it operates on that something. So X is the only example from this table that satisfies this for all criterion. Everything that X acts upon, whether it's left side or right side, remains the same. All right, how about commutative? We can ask this one as sort of some low-hanging fruit because a number of you addressed this property on daily work, even though it wasn't asked for on the daily work because you mixed up associative and commutative. It happens. Can we tell whether or not this operation is commutative by looking at the table? We can tell. How can we tell? Is it or is it not commutative? It's not commutative. Why? What are you looking at that shows you that it's not commutative? YZ. Mm-hmm. Yeah, Y times Z is equal to Z. But Z times Y is different from Y times Z, right? These two are not the same. And remember, the shorthand, when you have a multiplication table, is to look for symmetry across the main diagonal, right? And we have symmetry here and here. We have it here and here. We don't have it from there to there. Right? And because of the for all clause that's implicit, but we need to start making these things explicit, commutative would say for all A and B, we have A star B is equal to B star A. But for a universal claim, for a for all, how many bad apples does it take to spoil a bunch? 1, right? A single counterexample takes down the whole universal claim, the whole for all. So Is this a commutative operation? No. Because y star z is different from z star y. Okay. Associativity. Because there's 27 different possibilities, I don't think we have time for me to turn you loose in checking all 27 of them. And plus, that's just busy work, let's face it. So why don't I give this one away? So try this combination with your group. So take 2 or 3 minutes and see if this combination, you come up with a reason to conclude this is or is not associative. And then I want to talk about these inverses before we wrap up. The first thing we discovered, I asked you to test this for associativity, and you found out that what? When the role of A is played by Y, the role of B is played by Z, the role of C is played by Y. Does this associativity equation hold? It does not. Right? Y star Z star Y, if I group the first two and evaluate, gives me Z star Y, which is Y. If I group the second two, Z star Y is going to give me Y, Y star Y is Z, so those two disagree. So this operation is not associative. It's not commutative and it's not associative. What cancels X? How'd you answer that inverse question? So X cancels itself, right? Because X was the identity. X cancels X. What cancels Y? Y cancels itself. What cancels Z? So this is sort of like that set symmetric difference example, right? Where everything cancels itself. Everything is its own inverse, right? But then what happens when I use the observation that xz is equal to yz? How did you cancel the z's out of that equation? Yeah, you just multiply by z on both sides. X star z, and then the z star z goes away. So you get x on the left, and what do you get on the right? Why is that troubling? Because x, at least as far as we know, x does not equal y, right? It looks like those two are behaving differently within this structure. X is an identity. Y is not. But then how could x equal y in that case, right? So the moral of the story, and kind of the big question in abstract algebra, the big question for us this semester, is if you just hand me some elements, can I make a setting in which we can do algebra, simplify equations, simplify expressions, and solve equations? If I try to do that with this structure, I get something that's verging on nonsensical, right? It doesn't have the associative property. It doesn't have the commutative property, but we can probably live with that. It has an identity. Everything appears to have an inverse. But the fact that it's not associative, and the fact that this happened, that x was somehow equal to y, even though they have different properties, this is basically garbage for us. We can't do meaningful algebra with this multiplication table, is the point. So we can't just throw our elements together within a multiplication table any old way we want. Right? So a good question might be, if you give me 3 elements, is there a way to fix this problem? Okay. Can I fix this multiplication table to make it associative? So that was the daily work 4 question, and maybe it's worth revisiting between now and our next class. If I try to fix this and make it associative, do I still have this other problem with x equaling y? And maybe another question is, how many different ways could I fix this problem? Are there multiple answers for taking 3 elements and putting them together into a multiplication table to give me a meaningful place to do algebra? So that's the question I want to end this with, because it's a question that's going to take us the whole semester to really even meaningfully begin to explore.